We started in session 1 with a look on some of the basics of perceiving the world, making simple decisions, and the involvement of mental representation. And now remember that cognition refers to things like perceiving, attention, memory, reasoning, and language. And now let's continue in session 2 with a look on attention. We already talked about how in cognitive psychology we view the mind and the brain as processors of information, analogous to the way a computer processes information. So technological advancements that led to the development of pure information processors like computers really influenced cognitive scientists and psychologists. Now, obviously, the concept of attention was already very common far before the computer era. And in fact, it has a history within philosophical discourse going back to the early 16th century. Nowadays, William James is typically quoted on his view of attention. And in short, he says, there are a lot of things going on in the environment at any moment in time, which all could cause different trains of thought. Now the mind selects one of all of those possible things to think about. And he then goes on to say that the mind therefore withdraws from thinking about those other things in order to properly pay attention to the chosen stimulus. Now, as we discussed in one of our sessions, the phrase taking possession by the mind suggests that the mind intentionally selects a stimulus. But the mind can also, of course, be taken possession of, in the sense that some stimulus in the environment draws your attention towards it, forcing you to take it in. In other words, there is a difference between exogenous and endogenous attention. Exogenous attention is the attentional shift caused by an external event, whereas endogenous attention is an attentional shift by internal processes. You can read more on this and things such as overt and covert attention in the mandatory reading material for the course. But for now, let's return to the brain processes information analogous to a computer processing symbols. So the way computers are limited in their processing capacity, it is conceivable that the brain is also limited. If anything, we all know from personal experience that our attention is indeed limited. Attention is a limited resource. Even in colloquial language, we say that we have to pay attention, almost as if it's some kind of costly thing. Selective attention is also known as a cocktail party phenomenon, and there are several famous studies from psychology that clearly display the limitations of our attention, which manifest as effects like inattentional blindness or change blindness. Now, I've put some links into the video description that take you to other videos which display these effects clearly. In fact, you'll probably discover that several of such effects will still work on you even when you know what they're about. It also means that the optimum strategy for allocation of attention is often a flexible one. So, if we're constantly bombarded by many different stimuli throughout the day, how do we select the stimulus that is relevant to us at that moment? Well, we would first need to identify the available stimuli to some level, and then put the relevant ones into our working memory for further processing. In order to research how people perform this step, we need to mimic the way we are bombarded by stimuli in real life. So take a look at the next slide. Well, most likely your eyes looked around the scene a little bit. Perhaps you read the graffiti here saying Tuft. And if I told you that I took this picture in Cambridge, Massachusetts in the United States, you might guess that there is probably an S under the graffiti here. After that, your eyes may have moved down to the left toward another area with a lot of contrast, after which you possibly identified the group of ducks here. But the point is, of course, that you did all of this over the course of maybe 2 seconds. So if we, as cognitive psychologists, want to study the way in which you process stimuli in a natural environment, rather than within an experimental cubicle, we need to find a way to match those real-life conditions while at the same time keeping them controlled enough to make inferences somehow. And now that's not an easy task, but we've been able to come up with some creative solutions so far. Well, what your eyes do in natural environments, when you're bombarded with all of these stimuli, this continuous stream of stimuli, is they make movements. Your eyes make very quick, rapid movements that are called saccades. And between those movements, your eyes briefly focus on specific points. And those focused moments are called fixations. Now, you make thousands of such saccades throughout the day and take in stimuli during those brief moments of fixation. And now we mimic those saccades and fixations in experimental paradigms called rapid serial visual presentations. Now, in such research, we ask participants to focus on a fixation point, thereby controlling the stimuli they're exposed to, while at the same time flashing stimuli at them in a very rapid fashion on that fixation point, which mimics the very brief exposure time stimuli get in real life. In other words, we're studying the temporal characteristics of attention here. A common effect observed in RSVPs is the attentional blink. Now let's try a simple attentional blink trial on ourselves to refresh our memory on how RSVPs work and what the attentional blink is about. So carefully focus your attention on the fixation point, and in a moment, a string of numbers will be flashed at you on that fixation point, but the string of numbers will contain 2 letters. Now, can you identify the 2 letters? Let's see. So did you spot the letters? They were A and B. Chances are you spotted the A but missed the B. Now this is called the attentional blink. Your attention catches the first target, in this case the A, but blinks and misses the second target, the B. There are several theories which attempt to explain why the attentional blink takes place. At the time of the making of this video, the rough explanation of the attentional blink is as follows. When your attention catches the first target, the target is put into working memory to be consolidated, so that it can later be reported. But while this cognitive process of consolidation on the first target is taking place, the second target appears. Now, because the first target is still being processed, the second target is now temporarily denied entry into working memory. And because it's denied access into working memory, because your working memory is still busy with the first target, the neural activity for the second target declines and is lost. So, once working memory is done processing the first target and access to working memory is opened up again, it is now too late to still consolidate the second target. Now we can see the attentional blink effect in these results very clearly. Now take a careful look at the data for lag 3. Now lag 3 means that the second target was the third item to be shown after the first target, and that it occurs roughly 300 milliseconds after target 1. Now it is this decline in identification of the second target at lag 3 that is called the attentional blink. That's the effect. But now, this leads to an interesting proposal. It means that if the second target were to be presented later in the string of items, It might be the case that now the consolidation process for the first target is done by the time we see the second target, meaning that the second target now does have access to working memory and can be remembered. And that is indeed the case. Take a look at the data for lag 7. The accuracy for both targets goes back up again. We also see that if there's a lag of 1, meaning that the second target is the first item to be presented after the first target, the accuracy is also high. Now the idea here is that a lag of 1 is short enough for both targets to enter into working memory together and be consolidated together. Now this higher rate of accuracy for lag 1 compared to lag 3 is termed lag 1 sparing. Now we also know that emotions can have an effect on the way we deploy our attention. Emotions can cause us to lose strong focus and so make our attention more diffuse and spread out. So this diffusion of attention by emotions can reduce the attentional blink if the second target is emotionally relevant. So, if target 2 is emotionally relevant, it can diffuse our attention so that we aren't too focused on target 1, but save some attentional resources for the processing of target 2. Now, emotional relevance can take many forms, so we have to be a bit more precise than simply saying emotionally relevant. For example, positive emotions lead to more diffuse attention, but negative emotions tend to increase focus. So in these scenarios, what effect would positive emotions have on the attentional blink? And what effect would negative emotions have? Think about that for a moment. Now, if you said positive emotions lead to a more diffuse attentional state, and so they will reduce the attentional blink, you'd be correct. Now, the opposite is true for negative emotions, which often increase attentional blink. Now, this processing advantage that emotions have suggests that emotions are very fundamental to how we deploy our attention. In short, emotions can modulate the attentional blink via subconscious processing. Now, in the second sentence of William James's quote, we see that attention is the ability to withdraw from information that is irrelevant in order to effectively process information is relevant. But as we're about to find out, irrelevant information still influences our information processing, sometimes helping you and other times confusing you. Now let's continue with something called the Simon effect. This task belongs to the family of conflict paradigms in which irrelevant information relating to the stimulus still influences the accuracy and speed of your response. Now, before continuing, we should go over the different stages of responding to a stimulus. You must first identify a stimulus, then select the appropriate response, and finally actually implement your response. Now, as you may have guessed, the Simon effect is the effect that irrelevant information has during the response selection stage. So let's say that a green square requires a response of pressing the M key on the keyboard, whereas the red square requires a participant to press with the C key. Now that seems simple enough. But what if we now add some information into the trial that doesn't affect what responses are required? For example, we can put the stimuli either on the left or on the right of the fixation point. And again, just to be clear, the location of the stimulus does not matter, because the green square still requires the M key as its response, and the red square requires the C. So the location of the stimulus is the irrelevant information. But now we can define 4 categories of outcomes, 2 for each stimulus location. The stimuli can appear on the same side as the desired response or on the opposite side. After all, relative to each other, the M key is on the right and the C key is on the left. So a trial where we see the red square on the left, we press the C key, which is also on the left. Now this is called a congruent trial. If the red square were to appear on the right, our response is still the C key on the left. But now the location of the stimulus and the location of the response no longer congruent to one another. In other words, this is an incongruent trial. Now, as you may have guessed, the stimulus location, although irrelevant to the response selection, still influences the speed and the accuracy of a response. Congruent trials are often faster and more accurate than the incongruent trials. But why is that the case? Now, the original interpretation was that the congruent trials have a direct neural link. The stimulus on the left ends up being processed by the right hemisphere, and the right hemisphere is also the side that controls the left hand. Okay, good, we're done. That was simple enough, right? There's a more direct neural connection than in the incongruent trials, because in incongruent trials, the other hemisphere is the one controlling the responding hand. Now, at first, this seemed like a very good explanation. But now, here's the wonderful creativity of cognitive psychologists. If this direct neural link hypothesis is correct, we should be able to reverse the Simon effect by simply reversing our hand position. After all, if you were to perform the Simon task with your arms crossed, it is the incongruent trials which should then have the direct neural connection. And that's why you all perform the Simon task twice, once with your arms held straight and once crossed. So now let's take a look at the data to see what we found. Now we found a main effect of having your arms straight versus crossed. In other words, the response times were different between the arms straight condition versus the armed cross condition. Crossing your arms matters, and you're often slower when performing the task with your arms crossed. But that in and of itself isn't really all that interesting of a result. The second result is a little bit more interesting. That is the main effect of congruency versus incongruency. Now this is the effect that we call the Simon effect, and it is one of the most robust findings in psychology. It is highly influential in the way we design things like operators for machinery, user interfaces for software, dashboards and buttons in cars, and in cockpits of airplanes. I mean, let's face it, if you need to suddenly make a split-second decision, every millisecond counts. But the final effect here is perhaps most interesting. It is the interaction between our main effects. And it is actually not significant. Now, what does that mean? It means that crossing your arms has no effect on which of the two congruency conditions is faster. In other words, the congruent situation is always the fastest condition, regardless of the hand that you use. But how is that possible? The direct neural link hypothesis suggested that there should be an interaction. If your arms are straight, the congruent trials have the direct neural link, so that's why they're faster. But when you cross your arms, the incongruent trials have the direct neural link, so now they should be faster. But they're not, and that's the point. So what does that say about the direct neural link hypothesis? Well, it means that the direct neural link hypothesis that attempted to explain the Simon effect is wrong. So just to be clear, the Simon effect is very real and one of the strongest findings in psychology. The original theory that tried to explain the Simon effect proposed that there was a direct neural link in the congruent trials. But this means that the Simon effect can be reversed if we cross our arms. After all, if you cross your arms, the incongruent trials should now have the direct neural link. We tested this explanation for the Simon effect, but we found that the congruent trials were fastest in both conditions, arms crossed or not. Clearly, the Simon effect must be explained in a different way. Now, cognitive psychology is still trying to figure out why the Simon effect occurs. But in general, we feel that it is the result of the way the brain represents the information in its environment and the way in which it represents its responses within that environment. If there's an overlap in those representational codes, this can speed up responses, whereas conflicts between spatial representations of stimulus and response can create conflict and thereby slow down processing. So, the effect is assumed to be the result of a link between spatial representations, which are relevant for focusing the attention on the stimulus, and spatial representations which are relevant for motor preparation and execution. So the spatial location of the stimulus may be irrelevant for the response selection, but it is relevant for the process of deploying attention. So information that is relevant for one cognitive process can be irrelevant for another cognitive process. Attention is working with its own spatial representations, and your response processes are working with their own spatial representations. And those representations are technically irrelevant for the other process, but can still influence the other process if those spatial representations have some kind of overlap. Now, another famous effect in psychology is the Stroop effect. It is the difficulty that people experience when stating the color that a word is printed in if that word itself is a different color. So in the upper example, someone would respond with red, whereas in the bottom example, they would respond with green. Now, as you probably guessed, people find the top one difficult and the bottom one easy. So again, we see how irrelevant information can interfere with our response selection process. Even though the actual word itself is irrelevant information, it still influences the speed and accuracy of our responding with the color that the word is printed in. Now, Stroop originally stated that this interference was due to the automatic reading processes that take place. In other words, even though you know very well that the word itself doesn't matter for the task, you can't help but still get the urge to read the word. Now, it should be noted that there is some disagreement on whether the Stroop effect interference occurs in the stimulus identification stage or in the response selection stage. Now, our faculty at Leiden University holds the opinion that the Stroop effect is a type of interference that occurs at the response selection stage, just like the Simon effect. We already discussed assignment 4.3 within the section on the Simon effect. So now let's take a look at assignment 5.2. It asks us the following. When the colors must be named by saying them out loud, subjects often have more difficulty with the incongruent words than when they must press keys, as you did in the experiment. Now give a possible explanation for this phenomenon. So there are different versions of the Stroop task. For example, responses can be given by pressing keys that represent the colors. For example, you see the word green printed in the color red, and so you press the R key on the keyboard for red. But there's also a version of the task where the responses must be said out loud. In other words, now you would say red out loud, instead of pressing a key. The question basically asks why the spoken version of the task is much more difficult for people. Well, throughout this video, we've been talking about the steps that must be taken to turn a stimulus into a response. You identify the stimulus, you select the response needed for that stimulus, and you execute the response. So essentially, you selected the needed response based on some kind of response rule. In other words, I see the word green printed in red, I identify that the stimulus is the color red, and I know that if I see the color red, that I have to respond with keyboard key R. So I apply the rule whenever I see the color red, and I execute the response, press the R key on the keyboard. Now turn to page 30 in your syllabus. Below the figure 4.2 of the Erickson flanker task, there's a paragraph on whether irrelevant information has a direct influence on the response or through its translation into a response with a response rule. Now also take a look at page 39. There it mentions that the Stroop effect is attributed to the highly automated and therefore difficult to suppress act of reading the word. Now, reading words is highly automated and activates a potential speaking response. So the short answer to this question is that there's probably a more direct translation from stimulus to response in the spoken version of the Stroop task because the automated reading caused by the stimulus speeds up the speaking response. Naturally, this then also means that there will be far more difficulty in the spoken Stroop when the trials are incongruent. In other words, because there's a more direct connection between the automated reading and speaking the response, it is more difficult to stop yourself from saying the word rather than the color that the word is printed in when the word for the color and the word itself are different. Now let's take this rule-based responding versus direct responding a step further. The conflict in information processing that happens in the spoken Stroop task is that people may be retrieving the word for a color while a different word is written out. So green is written out here, but before we respond, we first retrieve or remember or select the word red in our mind. And based on that word, we decide what response must be given. So when we replace the speaking of the word with typing a response, the Stroop effect isn't as stable anymore. We will still see the effect if the word for the color, in this case red, is still somehow involved in this process. In other words, if the word for the color still mediates between stimulus color and response keys. Now, in even more simple words, are people using the word for the color throughout the entire process? If in the typed version of the Stroop, people still first think about the word red before they press the key, then we would still see the Stroop effect. But let's be honest, participants aren't stupid, and as you probably noticed yourself, for many of you the effect wasn't really visible when you did the task in the classroom. So what often happens is that participants skip that linguistic step of retrieving the word for the color first, which can then be used to mediate the responses. Now instead, people find a more direct way to respond without thinking of the word red first. Now they start to associate the colors with keyboard buttons. So for example, they'll start to associate the color red with a button that's located on the right of the keyboard. And words printed out in different colors do not already have a strong association with different locations on the keyboard. Now in this situation, the Stroop interference is mostly lost because people have found a way that is more direct to respond. A way that doesn't require them to think about the word for the color first in order to apply the rule. Instead, they're using locations on the keyboard. Now in fact, in previous years, many students asked, so why don't you put colored stickers on the buttons? That would make the task a lot easier. Well, yeah, of course it would. The Stroop interference happens because reading processes interfere with the response that must be selected to be said out loud. And reading and speaking are strongly associated. Now, if we type the response, we lose that strong stimulus-response association, and the interference tends to diminish. But with the colored stickers, we'd be going even a step further. Now, it would be a color-to-color response task. In other words, a color-to-color matching task. We wouldn't have the competing response as in the spoken Stroop. We wouldn't even be working with non-associated keyboard locations to diminish the interference. No, we'd have a non-conflicting, strong association between stimulus and response. Now in this scenario, it is likely that there will be almost no Stroop effect at all, because there's pretty much no conflict left. In fact, there's a version of the Stroop task where people have to point to colors on the board. And in this version, there's basically no Stroop effect at all. Now, the previous answer should suffice when it comes to any kind of similar question you may be asked on the exam. And the following section is an answer that follows the same reasoning, but is just outside of the scope of this course. In other words, we're still looking at the difference between using a rule to respond versus finding a more direct way to respond. So how can you go even further than our previous answers? I mean, we saw that in the spoken Stroop, there is an interference because a conflicting stimulus has a strong association with the type of response that must be given, reading and speaking. Now we can avoid that interference by changing the type of response required. So rather than speaking, we type. Now automated reading processes have less of an association with typing. So we managed to decrease the Stroop effect. We could then decrease it further by making the responses more comparable to the type of stimulus given. For example, by putting stickers on the keyboard. Now that would turn the task into a color-color matching task, as we just talked about earlier. So what's left to change? Well, how about the feedback that we get from our response? Now, what I've been trying to convey during my sessions with you guys is that the brain is concerned not simply with giving a response. Rather, it is very goal-oriented and outcome-oriented. It is often concerned with the eventual outcomes of its responses. So this means that the brain also processes the feedback it gets after responding. Eventually, the brain can predict what kind of feedback it should get before it responds. Now that's that SOR response chain we've been talking about. The expected outcome precedes the actual response in the process chain. So we can manipulate the task in some way that creates overlap between the stimulus and the kind of feedback that the brain would expect, given the response type. For example, tasks with spoken stimuli, which require spoken responses, can lead to very quick processing, because the stimulus is the same as the feedback that the brain gets after its response. In both cases, there's something being spoken out loud and something being heard. So the more we get those two things, the stimulus and the expected feedback from our response, to overlap, the higher the situation is set to be ideomotor compatible. Now, before I go into ideomotor compatibility, I should state again that the term is not used in the syllabus and does not appear in the coursebook. Topics like ideomotor compatibility and ideomotor theory are outside of the scope of this course, like I said earlier. So it's unlikely that you'll be quizzed on the topic of ideomotor compatibility precisely. So the first two explanations for this assignment should suffice for now. This is an introductory course on cognitive psychology, so there's no need to worry about the exact details of ideomotor compatibility. Nonetheless, it is good to be familiar with this concept, and it helps to be able to see how we can change elements of the stimulus that we present to people, the type of response we require from them, and even the kind of feedback their response would give them. So what is exactly fascinating about ideomotor compatibility? Well, we learned that attention has a bottleneck, and that we're limited in our processing capacity of stimuli. We can't process everything at once, and so we must make a selection and respond to those stimuli we selected at the expense of potential responses to other stimuli. But what if I told you there's actually a way to bypass the bottleneck and respond to stimuli in a very fast and very direct manner? That is ideomotor compatibility. The more overlap between the expected feedback from your response and the stimuli given, the higher those are said to be ideomotor compatible. And that fast responding here can obviously create a lot of interference as well. So, to sum up, there are several ways to explain why the spoken Stroop task is more difficult, but the basic idea behind all of these explanations is still the same. The idea that there is a difference between using a rule to respond and responding more directly. In the spoken Stroop, we need to always think of the word of the color first, because we need to respond by saying the color. In the typed Stroop, we don't necessarily need to think of the actual word for the color itself first. Here we can find more direct ways to respond, which then diminishes the Stroop effect, as many of you saw when you actually did the Stroop effect in the practical. So we are manipulating the type of response we want to get from the participant, and that manipulation changes the extent to which the Stroop effect occurs. Now, if we want participants to type, they no longer need to involve the actual words for the colors themselves in their responding anymore. But we can also go a step further and manipulate the type of feedback that a participant would get from their response. If this feedback is highly similar to the original stimulus we presented them with, we'd be bringing back the interference. In this last scenario, we'd be increasing something called ideomotor compatibility. Although this term is outside of the scope of this course, it is helpful to know for future courses. Well, I hope you enjoyed the video for session 2, and I'll see you in the video for session 3.